Okay, welcome back to EE210B, our course on inference over networks. And today I'm going to start part 2 of the course. Okay, part 2 deals with single agent adaptation and learning. In part 1, we covered background material, right? I covered concepts related to how to compute gradient vectors, Hessian matrices, for both cases of real arguments and complex arguments. We talked about convex functions, strongly convex functions. We talked about mean value theorems, Lipschitz conditions. We reviewed some basic matrix results, right? So these are all tools that we'll be using throughout the course. If you did not follow some of this material, don't worry about that. First, it is in the text. And second, whenever I need it, I'm going to remind you. Okay? I'm going to remind you of these. Some of them we'll be using them today. Okay? So that's part 1 of the course, background material. Okay? Concepts that I need throughout this course. Okay? So today I'll start the second part, which deals with single agent adaptation and learning. So you might say this is a course about information processing over networks, a collection of agents. So why am I talking about single agent adaptation and learning? Adaptation and learning by a single standalone agent. Okay, that's because the way I'm going to present this material will be useful for us to extend the results later to the network case, number 1. And number 2, I would like to develop results in this case so that later we can compare against the single agent performance and see how much better we can do, or sometimes how much worse we can do, right? So this will be useful for us as a frame of reference, okay, to compare performance by networked agents against single agent adaptation and learning. And in the meantime, many of the concepts that I will introduce in this lecture and in the next lecture will be extended to the network case. So if you understand them here, that will help you follow the arguments that we will see later, number 1. But also another point that I would like to make is that you will also see the challenges that we will face when we try to extend results from the single agent case to the network case. Not everything will be straightforward. Some of the concepts and some of the results will be more demanding. And if you understand this case, then you will appreciate more the challenges that you will face in the multi-agent case. Fine? So these are the reasons why I spend time talking about the single agent case. Okay? So that it serves as a frame of reference, and you will understand better the transition to the network case, and you will appreciate better the challenges that we will face and what new forms of dynamics come up when you move to the network case. Fine? Very good. Okay, so the lecture today is based on chapter 2 from the text. Okay, so that's chapter 2. We covered chapter 1, that was motivation, and we covered the appendices, that was background material. So now we move on to chapter 2. Okay, so what I'm going to be doing today, I will cover the class of, I think this doesn't work well with this, so let me stay with this. Okay? Okay. So I will cover the class of gradient descent algorithms. Now, those of you who took EE210A last quarter, that was a course on single agent adaptation and learning. You have seen some of this, but it will be more general here. Okay, I will discuss it in greater detail here. Over there, we focused largely on mean square error costs, for example. Okay, LMS type algorithms. Here, it will be a little bit more general. Okay, so this class of algorithms is very popular and very powerful and very simple and very efficient. Of course, it also has its disadvantages. We will mention some of them as we proceed, but many of the insights that you need to know about iterative algorithms, you can gain them by focusing on gradient descent algorithms. Okay, as always, I will focus first on the case when the arguments are real, and then extend the results to the complex case. Okay, very good. So let me first define what risk and loss functions are. And by the way, different terminologies are used in different fields. Some people call the risk function the cost function or the objective function. Okay, so you may see different terms used to refer to the same quantity. Okay, so what is a risk? Okay, so I'm going to use the notation j of omega to refer to the risk. So this is a function of a vector argument omega. So that's the cost function that I would like to minimize. Okay, I would like to find the minimum of j of omega. J of omega, the cost itself is always real valued, regardless of whether the argument omega is real or complex. Okay, for now I'm just talking about the case when omega is real. Okay, but the function itself will always be real. Okay, so this function is called a risk. We call it risk. Sometimes you hear the name cost, utility, or risk, right? So that's the function that I would like to minimize. Find the omega that minimizes this function. This function will be assuming it to be strongly convex most of the time. Okay? And as you know, strongly convex functions have a unique, right, minimum, and it's actually a global minimum. So the problem of finding the minimum of j of omega is well defined. Of course, this requirement of requiring the function to be strongly convex can be relaxed. But most of the time in this course, I focus on the case when the function is strongly convex in order not to deal with very technical situations. If I introduce the concepts to you in that context, you will get most of the ideas, and then you can extend it to other situations that are more technical, okay? So this is the risk function. Most of the time for us, the risk function will have this form. It will be the expectation of some loss function. So I use the notation Q for the loss function, J for the risk function, okay? Now, of course, if I'm defining J to be the expectation of a Q, it has to be the expectation over something, right? Omega is a deterministic variable, is a variable that you're trying to find. So often Q will depend on some data, which I'm denoting by the bold-faced letter X. I use the bold-faced notation to denote random variables, okay? So that's expectation over whatever data you have. I will be giving you examples very soon. Okay, so for example, Q could be a quadratic loss function like in mean square error. Q could be a logistic loss function, right? Like in logistic regression and so forth. Okay, and in learning, there are many other choices for Q, right? For example, we saw examples when dealing with perceptron loss or support vector machine loss functions and so forth. There are many loss functions that can go in here, okay? I'll give you an example very soon, but this is the general formulation. I have a risk function, which is the expectation of some loss function, and the expectation is over the distribution of some data. And I would like to minimize J. Now, in this course, we're interested in not only in optimization, which is optimizing J, and that's what we are going to be doing in this lecture, but in a future lecture, in the next lecture, I will be interested in a situation where I actually do not know J. Because to know J, you need to know the distribution of the data to compute the expectation. There are many problems, and that's normally the case in adaptation and learning, where what you know is Q. You don't know J. You know Q, and you don't know the distribution of the data. So in that case, you cannot compute J. So how can you converge close enough to the minimum of J under that situation? So that leads us to the context of stochastic gradient algorithms for adaptation and learning, which I will be discussing in a future lecture. Today, I'm assuming that I know J and I would like to minimize it. So today is the deterministic optimization problem. Today is an optimization lecture, right? I would like to minimize J, find the minimum of J. Okay? So Q will not play a major role today, but next time it will, okay? So some notation, you already know about this notation. I'm going to denote the gradient vector of J relative to omega. Now omega is a column vector in my notation, so the gradient relative to a column is a row, and it will contain the partial derivatives relative to the individual entries of omega. Remember, this was our definition of the gradient vector, okay? And if you compute the gradient relative to the transpose of omega, omega transpose is a row, so that gradient becomes a column. It is the transpose of the previous gradient vector, right? So this is just a reminder of how we define the gradient vector of J. Okay? And these partial derivatives are computed relative to the individual entries of omega, which I'm denoting them here by this notation, okay? And then I also define the Hessian matrix of J. Since omega is real value, the Hessian matrix is m by m. And how do you get it? You simply compute two successive gradient operations, right? The gradient relative to omega, and then relative to omega transpose, or the other way around. It doesn't matter which operation you do, right? You can do this first and then that, or this first and then that, okay? So these are definitions we saw before. Examples before we talk about gradient descent algorithms for solving that problem. This is the mean square error case, okay? So here I have, let's assume I have a random variable d, a scalar, a row vector u, called a regression vector. Okay, so that will be my convention for regression vectors in this course. They will be row vectors, u. So d is a scalar random variable. Let's say it has some variance, expected value of d squared denoted by sigma d squared. I'm assuming all random variables are zero mean, right? That without any loss in generality, you can assume that. And the covariance matrix of u is denoted by ru. Since u is a row, u transpose is a column. When you compute the expected value of that, you get a matrix which I'm calling ru, and I'm assuming it is positive definite, okay? So I have random variables d and u, and what the mean square error problem does, it formulates this problem here. I would like to find the w that minimizes the mean square error between d and uw, right? So you can think of u times w, that's an inner product, row times a column, as an approximation, an estimation for d. And you would like to find the omega, right? The difference is the error. The difference squared under expectation is the mean square error. You would like to find the omega that minimizes the mean square error, right? That's what the mean square error criterion is. So if you expand it, right, so you will get, for example, expected value of d squared, that's sigma d squared. If you expand the last term here, you will get w transpose expected value of u transpose u w, which is this last term here, and so forth, right? So you can expand it, you will get this expression here, and you can see from this expression that it is quadratic in omega, right? Okay, quadratic in omega. So J is the risk, and what is Q in this case? What is the loss function in this case? And what are the random data X that I called before X? They are D and U, right? D and U. So in this case, this is D minus UW squared, right? It's a function of the unknown, but it depends on some random data, D and U, and over which you take the expectation to find the risk function, right? You see the analogy, okay? We are going to be using the mean square error cost many times in this course, so I would like you to understand it, okay? So this is one example, okay? So here it is. This is the loss. X is D and U in this case, okay? If you compute the gradient of J, what's the gradient of J relative to omega? So it has to be a row vector, right? So it will be 2 omega transpose RU, right? And here minus 2 RDU transpose. And the Hessian, 2 RU, right? So that's it. Okay, you are experts by now, right? Okay. And by the way, if you want to plot it, this is a plot of that quadratic function over two-dimensional space. Capital M is equal to 2, right? So omega only has 2 entries, so that you see how it looks like, right? In one dimension, it will look like a parabola. In 2 dimension, right, it has this shape, and it has a unique minimum, okay? Very good. This is one example. Let's look at another example, right? The logistic risk. Here it is. Remember, I had a lecture before where I explained to you how this cost function, this second term here, comes up in the context of logistic regression. So what was that problem? Over there, I have a collection of random variables gamma. This random variable assumes values plus or minus 1 with a certain probability, right? P1 minus B. And I have regression vectors or feature vectors H. That's the terminology now for H. So H is a feature vector, okay? And with covariance matrix R sub H, as you see here, R sub H, in the logistic regression problem, I would like to minimize this risk function, which is defined in terms of the expected value of the logistic loss, right? Log, and here the random variables appear in the exponent of E, and this is a regularization term, right? This is a regularization term. You are putting some weight on the energy of omega, right? On the squared Euclidean norm of omega. What regularization terms like this try to do, if you are trying to minimize J of omega, they are trying to discourage omegas that have large values, right? Whenever you add a term like this, you are essentially bounding the size of the resulting omega that you are looking for. So regularization is useful for that purpose, okay? Here it will have another purpose as well. Remember that the logistic risk is very useful, for example, in machine learning problems, in pattern classification problems. I give you a collection of data, right? Let's say many gammas, many H's. For each feature vector, I tell you it belongs to class +1 or class -1, right? Let's say I gave you the example where the entries of H could be your height and your weight, and gamma could be whether you are a female individual or a male individual, right? I give you a collection of gammas and H's. You use the training data. You use this data as training data to find an omega. That omega, you are going to find it using a gradient descent, a stochastic gradient descent algorithm in the manner explained in the next lecture to minimize a cost function like this. If I just give you the data, I'm not giving you the distribution of the data. I'm just giving you real data, right? So you don't really know how to find the minimum of this J, but you can approximate it using a stochastic gradient algorithm of the form we will study next time. So given the training data, I can come up with an algorithm that approximates that minimum and converges to some solution, let's call it omega O. Once you have this omega O, if I give you a new H, what you do, you take this new H, you compute the inner product of it with the minimum you found, with the minimizer you found, and whether this is larger than or equal to 0 or less than 0, you attribute that feature vector to one class or the other, right? That's how logistic regression works, like I covered in a previous lecture, okay? But don't worry about this for now. This is just an example. For now, just think of this as a function, as another example of a risk function, okay? And I'm interested in finding its minimum. Why? Because it has applications, for example, in pattern classification problems, just like I explained, okay? Very good. Now, you can compute the gradient of this, right? The gradient of the first term here will be rho omega transpose, gradient relative to omega, right? And here, assuming you can switch the expectation with the gradient, you can find very easily what the gradient of this log function is, right, relative to omega. This is a simple calculus question, right? So if you do that calculation, I have the expression here. I'm showing you the loss before that. This is the loss. So I just removed the expectation, right? I removed it. Okay? And yes.
Are we assuming omega is real?
Yeah. For in this first part of the lecture, I'm assuming omega is real. Later in the lecture, I'll go to the complex case, okay? So if you compute the gradient and the Hessian, you're going to get these expressions here, okay? Fine so far? Now, look at the expression. What was the Hessian in the quadratic case? 2RU. Is it positive definite? And it is larger than 2 lambda min of RU. So the function there, when RU is positive definite, is strongly convex. What about the logistic regression function I just showed you here, the regularized version of it? Look at the expression 12, right? This quantity here, you see H transpose, H is a column. This is like a covariance. This is always non-negative. H transpose is always non-negative. This ratio is always a number that's non-negative, right? So under expectation, this quantity here is always non-negative. And you are adding to it rho I, right? So this quantity here is always non-negative. So you know that this is strictly larger than rho I, right? Sorry, strict larger than or equal to rho I, which is larger than 0. So it is strongly convex, right? With the factor nu that we use to define strong convexity being equal to rho. And that's one of the reasons why we added rho here, not just to control the size of omega, but to ensure that we have a strongly convex function so that the problem has a unique minimum. Fine? Very good. And if you want to plot what this logistic regression function looks like, this is one example of it. Okay, again, it's very much similar to the quadratic case, right? The shape of it. Okay, good. So you know what risk functions are, you know what loss functions are, and I reminded you of the logistic risk and loss. Now, before I continue, this is something I covered last time, right, or I mentioned briefly last time when I was reviewing matrix results. The big O and the little o notation, we'll be using that a lot in this course. I just want to make sure you understand it. Okay, so I will be using this notation in two ways. Okay, they are, of course, related, so I'm summarizing them in this slide. Okay, so what is the big O notation? So if I have, so here, this is the big O notation, this is the little o notation, okay? If I have two sequences A and B, then I will say that A is big OB, that's first thing here, okay? If A and B are essentially comparable, right? If A and B, there is some constant that bounds, let's say, the entries of A by the entries of B, and that constant is independent of I, okay? So that essentially means they are comparable. Okay, they are comparable up to some constant. Of course, one can be 1,000 times the other, okay? But if B scales, A will scale similarly, okay? So for example, when I write something like this, A of I is of the order of 1 over I, you are saying that the samples of the sequence A of I, right, they behave like 1 over I. So they are converging at a rate that's comparable to 1 over I. Right? Because 1 over I is going down to 0. The samples of A of I will be up to some constant of that same order, right? So they will also be going down to 0 at that rate. So when you see A is big O 1 over I, it means that A is comparable to 1 over I, is behaving and going down to 0 at that rate, right? Okay. Little o means that when I say A is little o 1 over I, it's going down to 0 at a faster rate than 1 over I. For example, 1 over I squared, okay? Or 1 over I to the power 1 plus epsilon. That's already little o, okay? More formally, when I say that A is of the little o B of I, it means that the ratio goes to 0, right, as I goes to infinity. So for example, if B is 1 over I is going to 0. Right? A should be going to 0 faster, 1 over I squared, for example, so that this ratio goes to 0 as I goes to infinity, okay? So for all practical purposes, what this notation really means is that if I say that something, let's make it constant now. If I say that something is big O mu or little o mu, big O mu, you mean that A is of the same order as mu, okay? Same order as mu. Little o, it means that this A is a higher order power of mu. So why is this useful? Because for example, sometimes I will write expressions like this. X is Y plus big O mu. Or X is Y plus little o mu. What this is saying is that the error, that Y is some approximation for X, and the error, right, is of the order of mu, right, is of that order, or a higher order of mu, for example, mu squared, mu cubed, right? That's what this notation means. They give you the size or the order of the error, right? That's when you use it in this context. When you use it in this context, you are saying at what rate. So here you are saying A of I is converging at a faster rate than 1 over I, or at a comparable rate as 1 over I. You understand this notation? You will see this notation here at the bottom of the slide very often. You will see the first two notation comparing to, relating to convergence rates today, okay, in this lecture, okay? So, very good. So let's move on. Now you know what risk functions are, you know what loss functions are, okay? So what are the conditions that we need to introduce on risk functions before I can prove convergence of the gradient descent algorithms for this lecture, okay? I will be introducing some conditions. Again, these conditions are stronger than necessary. You can weaken them. In some of your homework problems, I'll ask you to weaken some of these conditions. But you can go even further, okay? But like I said before, the purpose of this lecture is not to make it as technical, or of this class is not to make these statements as technical as they can be, but to convey to you the main ideas, the key concepts, okay? And then if you want to weaken the conditions, you will be able to follow the arguments because you have already seen the core of the arguments here, okay? So what are the conditions that I need to introduce on the risk function? First of all, this is the problem I would like to minimize. The first condition is that I would like J to be strongly convex. The main motivation for that is because that problem will have a unique minimum, okay? So I'm going to assume that my function, like you see it in this equation 14, is strongly convex. We already know that that means the Hessian is bounded away from 0 from below, right? By some nu. Okay, and this will mean that your function will have a unique minimum. So that's condition number 1. Throughout this course, you will see conditions like this, okay? Condition number 1, strongly convex, okay? Now, it's not just because you will have a unique minimum that I'm interested in strong convexity. There is actually a little bit more, and you will see that in today's lecture. Here I'm just stating them. The proof of these results, or of at least the last part of this statement here, you will see it later in this class. Another main motivation for using strong convexity, besides having a unique global minimum, is this fact. I'm going to develop an algorithm, an iterative algorithm that goes from one estimate for WO to another estimate until you converge to it. And then because of strong convexity, you are going to see that this algorithm has geometric or exponential convergence. What it means, it converges, the error, okay, converges at an exponential rate. Alpha is a number less than 1. Okay, it will converge exponentially, right? If you have here, for example, 1/2 to the I, and you plot that sequence, it converges exponentially fast to 0, right? Okay, so what I'm saying is under strong convexity, your algorithm, the algorithm that we will be introducing, it will converge the error, okay, between the estimate at iteration I and WO that you are trying to find. That error will converge at an exponential rate. Strong convexity will ensure that, and I will tell you what this alpha is. I'll give you the expression for alpha, okay? And it will be less than 1. So this is one thing that will follow from strong convexity. If, for some reason, you only assume convexity, in that case, you still have only global minima. You may have multiple global minima, but often that doesn't really matter because as long as you converge to a global minimum, that's good enough. So convexity alone only ensures that the Hessian matrix is non-negative definite, right? Not necessarily further away from it, okay? But then, if you study the convergence rate under convexity alone, what you will be able to see is that you can only ensure convergence at the rate 1/I. So which one converges faster? Exponential convergence or this convergence? Exponential, right? So the convergence rate will take a hit, right? If your function is only convex, the algorithm will converge at the rate of 1/I. Strong convexity will ensure a faster rate of convergence, okay? So that's useful, okay? Now, how do I ensure strong convexity? It's not always the case that you have strongly convex functions, right? For example, if you go to the logistic risk, remove the regularization term. Remember, I showed you it is rho of I plus something non-negative, right? That something in general is non-negative definite. It's not necessarily positive definite, right? Okay? Or bounded away from 0 from below. But when you add regularization, it becomes strongly convex, right? Okay, so very often by adding regularization, by adding a term like this, for example, even in the quadratic case, let's assume RU is singular, not necessarily positive definite, but non-negative definite. RU is singular. Will this second term here, this mean square error, be strongly convex? What's the Hessian? 2RU, right? It's not necessarily strongly convex anymore. You can make it strongly convex by adding this regularization term, right? Because the Hessian matrix in that case will include a new term which is rho I, right? And rho I, even if this is non-negative definite, the RU is non-negative definite, rho I will make it strongly convex, right? And that was the same thing we did for the logistic loss. We added a regularization term. So very often, actually, in practice, it's not uncommon, right? And you saw some of that when we were talking about learning algorithms in EE210A. You saw all types of regularization used frequently. It's not uncommon to use regularization in the context of adaptation and learning. And so regularization helps ensure strong convexity in many cases, okay? So this is not a strict requirement. You already have it there, okay, for you to use. Let's continue. Yeah?
If we have a convex function,
yes,
then theoretically we can still apply Newton-Raphson's method, which is
yes.
Supposed to be convergent exponentially.
Yes, okay. Now, like I said, okay, I will not be talking about Newton's methods, okay? But you will be dealing with some of it in your homework problems. Now, for Newton's method, you often rely on the inverse of the Hessian matrix, right? So this is another advantage of having a strongly convex function. This Hessian matrix will be well conditioned. Its smallest eigenvalue will be bounded away from zero. That's not necessarily the case when you have only convex functions. You may end up with an ill-conditioned algorithm, okay? It is true that you can use Newton's methods to speed up conversions, okay? But like I said, I'm focusing in this lecture on gradient descent algorithms. Many of the ideas can be extended to Newton's methods, and you can do that, and you will be doing some of that in your assignments, okay? Yes.
So for strongly convex problem,
yes.
The more that we are bound away from zero, does that mean the faster the convergence?
Okay, I'll give you the expression for alpha, and then you will see, okay?
Professor?
Yes?
When you get 1 over k raised, do you need the assumption that Lipschitz coming here?
I'm getting there. I'm getting to the Lipschitz, okay? Here I'm giving you high-level summary of what the result will look like. I'm not getting too technical. I'll get more technical very soon, okay? Okay. Very good. So I need strong convexity. Here it is, right? I also need to introduce a Lipschitz condition on the gradient of the function, okay? A Lipschitz condition. Remember, I explained what this is last time. A function is Lipschitz. In this case, the gradient is Lipschitz if there is some delta that makes this inequality hold, right? Okay? Small changes in omega, some changes in omega. If you change omega, the gradients will change in a bounded manner like this. This is a very useful condition. Again, we will be using it, okay? Now, because the function, we assumed it is strongly convex, then the Hessian is bounded from below, correct? And because the gradient is Lipschitz, remember this was one of the key results from the last lecture when I talked about Lipschitz conditions, that the Lipschitz condition on the gradient is equivalent to the Hessian being bounded by delta, right? And I gave you an intuition for that. If you just divide this by that, this looks like, right, the ratio of a derivative, right? You understand that? So that's why I'm going to assume this condition in today's lecture. When I tell you the Hessian is bounded from below and from above, I'm essentially telling you the function is strongly convex and the gradient of the function is Lipschitz, right? So I don't need to say all of that each time. I just need to tell you, assume that the Hessian is bounded from below and from above. Fine? Okay, so now you understand where this condition comes from. Okay, Lipschitz gradient, strong convexity. Okay? Now, what about, let's go back to the examples that we have. I have them in the next slide. Maybe I can go to the slides, okay? Let's look at the quadratic case. What was the Hessian in the quadratic case? 2RU. It's bounded from below by 2 lambda min of RU, from above by 2 lambda max of RU. So the quadratic case automatically satisfies that condition, right? Let's go to the logistic regression problem. We already know that from below, it's bounded by rho. And from above, it will be bounded by rho by plus that second term that's there. One of the homework problems I ask you to show that matrix there is bounded by the lambda max of RH. Well, if it's not that difficult to see, because that term was something like this: expected value of H transpose, which is a covariance, times a ratio which was always less than 1. Right? It was a ratio, right? An exponential over 1 plus the exponential, a ratio that was always less than 1. So it's not difficult for you to conclude that this term here is upper bounded by the maximum eigenvalue of H transpose under expectation. Okay. So in the logistic case, the condition is also satisfied, right? And there are many other examples. These are not the only examples, but I'm using them here to motivate, okay, the derivation. Okay, very good. So these are the conditions, okay? This assumption here, 2.1, is just restating the condition. I'm assuming that I have a function j that is strongly convex and its gradient is Lipschitz, okay? That's what this statement is saying, referring to the conditions by means of equations, okay? This is spelling it out, okay? So I'm assuming that my function is twice differentiable. Why? Because I'm imposing conditions on the Hessian, so I need it to be twice differentiable. Again, I said you can relax these conditions, okay? For example, you can work only with the Lipschitz condition on the gradient of J, right? For example, that's one way to do it, right? You can work with this condition. Instead, we are going to work with this condition because I assume the function is differentiable, under which these conditions are equivalent, okay? And strong convexity. So this is the lower bound, this is the upper bound. Fine? And these conditions, A, B, C, they are satisfied at least by quadratic or logistic risks, but there are other risks, okay? Here it is. Okay, I'm just repeating what I just said. For quadratic risks, it's satisfied, and for logistic risks, this condition is satisfied. Okay? So this, again, is summarizing this part. So under these conditions, we are going to devise an algorithm that minimizes J of omega iteratively. That algorithm, I'm going to show, it will converge to the global minimum, which I'm denoting by omega O, and the convergence will be at an exponential rate. The error, the difference between Wi and Wo, that error, okay, the norm of that error will converge at an exponential rate, okay, and strong convexity is useful, and it is attained by regularization. For example, it guards against ill conditioning. If you want to use a Newton's type algorithm, your Hessian matrix will be well conditioned, for example, okay? Very good. Okay? Now, for you to, of course, if your function is only convex, you can have multiple minima. The convergence will be at a slower rate, 1 over I. And here, for you to appreciate a little bit more the difference between exponential convergence and linear convergence, if your algorithm is converging at this rate, 1 over I, how many iterations will it take for this to reach an accuracy level epsilon? Right? The error is decaying at that rate. You would like it to reach epsilon. Epsilon, let's say, is 10 to the minus 6. You will need 10 to the 6 iterations, right? In the exponential case, you want alpha to the I to reach epsilon, right? Which means I, let's say ln of alpha is ln of epsilon. Now, this epsilon is less than 1, right? So ln is negative. And this ln of alpha is negative, right? So this tells you that I is essentially ln of 1 over epsilon, because you will have a negative sign when you remove the ln of alpha, right? So I need of the order of 10 to the 6 under ln. That's approximately 6 iterations, right? So convergence, so it's the convergence, the difference in convergence is significant, okay? Fine. So this is what risk and loss functions are, and the conditions we impose on the risk and loss function, okay? And they are satisfied in many cases. So let's now introduce gradient descent algorithms. What are these algorithms? And show that they indeed converge at an exponential rate, okay? So what is gradient descent? Again, there are, by the way, many types of iterative algorithms to solve problems like this. Newton type algorithms is another class, and there are other classes, okay? But in this course, I would like to focus on gradient descent recursions, because that helps convey most of the ideas you need to understand even these other algorithms. And because these classes of algorithms are efficient and simple, and I would like to focus on algorithms that are simple to implement. They do not require too much computational cost, okay? So a gradient descent algorithm looks like this. I would like to converge to the minimum of j. Okay? In an iterative manner. So the way you do it, you start from an initial guess, any initial guess, for example, the zero vector, and you start iterating. The new weight, the new estimate at iteration I is what you had at the previous iteration. You move along the negative direction of the gradient vector at that previous iteration. And the mu is a small step size, right? Positive step size parameter. So you start, okay? So you start from the previous estimate and you move to the new estimate, okay? So for example, in the scalar case, let's assume omega is a scalar. J of omega will be quadratic. And this is W at I minus 1. The gradient vector here, right? Let's say in the scalar case, the derivative there will point in the direction where the function is increasing, right? If you compute the derivative here, it will point in that direction, right? The vector will point in that. So you move in the opposite direction so that you get closer to the global minimum, which is here, right? That's the intuition behind this construction, right? We saw this construction in 210A. Here I'll talk about it more generally. There we focused largely on the case when this was a mean square error cost. And then we found conditions on the step size to ensure that it converges to the solution of the normal equations in that case. You remember that, right? I will be revisiting this example later in this lecture. But here I would like, for a general strongly convex function, under the conditions I stated, how can I ensure that this will converge? At what rate it will converge? What's the bound on mu to ensure that it converges, right? For general J, not just mean square error cost, for example, for the logistic cost or some other cost, okay? So this is the main result for this part, okay? Let me state it first. The result says, remember, nu is the lower bound on the Hessian, right? Delta is the upper bound. So of course, one is less than the other. So, okay, so it says that there is an upper bound on nu. So I read this usually in a different way, that as long as nu is small enough, the algorithm will converge. Okay, and the algorithm converges in this manner here. The squared norm converges exponentially fast. Where this alpha will be strictly less than 1. I'll give you the expression for it in the next slide. So this tells you that the squared norm, the energy is decaying exponentially fast. And what is the expression for alpha? So this is the lemma. It requires proof, okay? The expression for alpha, here it is, okay? The expression for alpha, it is 1 minus something, okay? So how do I ensure that this is always less than 1? Because this is minus here and this is plus. That bound I gave you on mu ensures that this will always be less than 1. I'm going to show you that, okay? The bound I gave you. And then coming back to your question, I'll show you a plot and then, okay, you'll see the answer to your question, okay? Fine. So I need to prove this result, right? I need to prove it. I'm going to prove this result in 2 ways. One is a traditional way, and the other may look more complicated to you, but actually it is this second way of doing things that extends more naturally to the network context. Okay, so I'm going to show you both ways. And then when we study networks later, you are going to see that the second way of establishing this result is the more natural way of extending results like this to the network context. Okay. Now, how would you, if you were to prove a result like this, how would you prove it? This is the algorithm. What would you do? Find the error, subtract WO, that gives you a W tilde, plus this mu, and now compute the square of that and show that the right-hand side can be written in the form alpha, the square of this, where alpha is less than 1, right? That's essentially what we need to show, and that's what we are going to do. Okay? So this is a different way of stating the result in a more compact manner. This is the algorithm. This is the algorithm. This is how I define the error, the difference between what you want and what you have at iteration I. And the lemma is saying that the squared error converges exponentially, and this is alpha. And what you have here additionally is the plot, because you see the expression I gave you for alpha depends on nu. Okay, of course it depends on the parameters nu and delta. These are problem dependent, right, on your function. Okay, so we have no control over that. But this is a quadratic function of the step size, right? So you can plot it here. This is nu. This is alpha of nu, right? If you plot it, you will see that the minimum of that quadratic function occurs at nu over delta squared. And the value of the minimum is 1 minus nu squared over delta squared. So this value of the minimum is positive because nu is less than delta. So it's above the horizontal axis. And when nu is 0, you get 1. And when nu is 2 nu over delta squared, you get 1. So you can see for values of step size less than 2 nu over delta squared, which is the condition I gave you before, this function will be smaller than 1, right? So now you can come back to your question. You can see, right, how you can study now how the value of nu, right, if you increase nu, right, if you increase nu, you are making your, of course, within bounds, right? This alpha becomes smaller, right? So the alpha becomes smaller, right? So this answers your question, okay? So let's go to the first proof. The first proof, again, I'm going to remind you of a result we established before. I'm only interested in the last line in this table. If a function is strongly convex, I showed you that this implies that this inner product between two different points and the gradients at these points, right? This is an inner product, right? Is always larger than or equal to the norm squared. We showed this, okay? This was one of the properties of strongly convex functions, okay? So I'm just reviewing it, recall number 2, right? So I'm going to use it in the proof now, okay? And the other result I'm going to use in the proof is the mean value theorem. I'm reminding you, remember, if I have a convex function, actually not just and this is true for any differentiable function, right? Difference in terms of the integral of the gradient, difference of gradients in terms of the integral of the Hessian, right? So I'm just reminding you that we saw this before. And if this z0 happens to be the minimum of the function, then the gradient disappears, right? Okay, very good. So you remember these results? So let's continue then. Let's go to the proof. This is the proof. This is the first proof. Okay, you will see it and then we'll move on to the second proof, okay? So if I subtract W0 from the recursion, you get W tilde, you get W tilde, you get plus, but I added this term here. What's the value of this term, this last term? It is 0, so I did not change anything. Now, why did I add this term? Because now I can apply the mean value theorem here, right? The mean value theorem on the gradient, right? Difference. If you go back, the mean value theorem on the gradient difference, it will be related to the difference, right? Plus something that depends on the Hessian. But the important thing, you will get the difference. So this will involve something that relates to the Hessian, but something also that relates to the difference. The difference is W tilde I minus 1, right? The difference between this and that, right? Then I will be able to group these two terms together. You see why that's useful? This is W tilde, this will be something times W tilde, I can group them together, okay? So that's, okay, so here it is. Okay? So the first thing I did, okay, if you go back, so this is the error recursion. Let's square both sides, right? This and this. Then you will get the square of this, the cross terms, and the square of the last term, right? This is just algebra. Here it is. You see the square of the first term, the square of the second term, right? And the cross term. The cross term, look here, the difference times the error times 2, right? Now, this last here, remember, J is strongly convex. This is an inner product of difference, of a difference times, right? The difference of, we know because of strong convexity, this is larger than, right? In U times the norm of W tilde squared. That's how I replaced it by, you see, I replaced it by that. So that's why you get inequality here, because I use that to do away with that. I want to put everything in terms of W tilde. So that's that. What about the second term up there? The second term, you apply the mean value theorem. The difference of gradients, you will have W tilde times something that depends on the Hessian, right? okay? Something that depends on the Haitian, okay? Here it is. But now I know that the Haitian is bounded by delta from above, right? So that's how you get this inequality here, because this integral will be bounded by delta squared. No matter what this Haitian is, I know this is bounded by delta squared, right? So you see each of the terms I was able to relate it to W tilde, and I'll put them together, right? Put them together, you'll get 1 minus 2 mu plus mu squared, that's the alpha, right? And that's exactly the statement of the lemma, that the error evolves in this manner for that alpha, right? And because the alpha is strictly less than 1 for the bound you imposed on u, it will converge. Fine? So that's the proof, okay? Because for nu less than this, alpha will be strictly less than 1, and therefore you converge. Fine? And the convergence is exponential. So that's proof number 1. Did you follow it? It wasn't difficult, right? So if your function is strongly convex, you can iterate the algorithm and it will find the minimum for you at an exponential rate, okay? So let me see now the second proof. Let me introduce the second proof. Okay. So let me first remind you of this other result, okay, which comes under matrix results for the spectral radius and norms of matrices. Remember I talked about matrix norms last time. I listed several of them. And I also talked about the spectral radius of a matrix. That's the definition. If A is some matrix, a square matrix, what is the spectral radius of that matrix? It has eigenvalues. They can be real or complex. Take the maximum norm. That's the spectral radius, okay? Fine. And this is the notation we will be using for the spectral radius of a matrix. Now, the spectral radius has these two useful properties. You can prove them as homework problems, not difficult to check. For any induced matrix norm, one norm, for example, is an induced matrix norm. The two induced norm, which is the maximum singular value. The spectral radius is always upper bounded by any induced matrix norm. This is a property of spectral radius. And then, if the matrix happens to be symmetric, its spectral radius is equal to its spectral norm. Okay, you should know that. The spectral norm of a matrix. What is the spectral norm of a matrix? It is the maximum singular value of the matrix, right? Right? If the matrix happens to be symmetric, they agree. The spectral radius will agree with the maximum singular value. Okay, so these are useful properties of, okay, the spectral radius of a matrix that you need to know. I'm not proving them, but it's not difficult to prove, okay? You can try them as homework problems, okay? This comes under the review of matrix results, fine? So I'm going to be using this result, okay? For the second proof. Here is the second proof. The second proof, again, you have the gradient recursion, subtract WO from both sides, you get 27. What's different between 27 and the previous error recursion? I did not add that additional. That's an insight. You may not have that insight, right? You may just get this. So let's persist with this, right? It's not always that you will think of an insight. Of course, it's a trivial insight in that case, but it's an insight. Somebody should have thought about it, right, for the first time. Okay, and then it becomes trivial. That's the problem usually with good ideas, right? Once you see it, it looks trivial, but it wasn't trivial the first time. Okay, fine. So I subtracted WO from both sides. You get this error recursion, right? Let's square, right? Let's square. Or before squaring, apply the mean value theorem to this gradient, right? Because the mean value theorem tells me this gradient minus the gradient at omega 0, which is 0, is an integral that depends on the Haitian, right? Here it is. I applied the mean value theorem, right? You will have the W tilde, which is the difference between WI minus 1 and WO, and the integral of a term that depends on the Haitian. It looks complicated, but I don't really care because we are going to bound it, right? Okay, we are going to bound it. So this integral, you will see this notation a lot in my formulations, right? This integral of the Hessian, I call it H. H, just to remind you of the Hessian, okay? And the subscript is I minus 1 just because it depends on data at time I minus 1, on the estimate at time I minus 1. So it's something that depends on I. It's changing with I, right? Because it has W tilde I minus 1 here. Fine? So you understand, okay, where this came from? And this is, you see, the integral of the Hessian, I'm calling it Hi minus 1. Okay. So now my recursion becomes W tilde I is W tilde I minus 1 minus mu times the gradient, so mu times Hi minus 1 W tilde I minus 1, correct? Right? Sorry, there is a plus here, right? Plus, but then there is a minus here, right? So it becomes minus here. So you can group them together, so you get that the recursion becomes I minus mu Hi minus 1 W tilde I minus 1, right? This is how the error evolves. But remember, this matrix H is also changing with I, right? If H were not changing with I, if it were a constant, for example, in the mean square error case, what is this Hessian? 2RU, right? Some multiple of RU, regardless of what W tilde is. The integral will always be a constant. It will be a constant here. So if this is a constant, it's very easy for you to come up with a condition on mu to ensure that W tilde is going to 0, right? Mu has to be less than 2 over lambda max of H. I'm going to do this example next, okay? But here, in the general case, this H changes with I as well, okay? So here it is. Well, let's compute the norms from both sides. The squared norm is upper bounded by the product of the squared norms, right? This is the submultiplicative property of norms. So now I would like to show that I can replace this by an alpha that's strictly less than 1, and that's it, right? Very good. Now H is symmetric, yes or no? It's symmetric. It's the integral of a Hessian, okay? So this is a symmetric matrix. I minus that is a symmetric matrix. So the 2 norm, this is the 2 norm that I'm using here. The 2 norm is the spectral radius. So I can replace this by the spectral radius of this difference squared, right? Fine. What is the spectral radius of I minus a matrix? It's 1 minus the spectral. Well, okay, let's do it slowly. Okay, let's do it slowly. Okay, here. Okay, let's do it slowly. Okay, because I have to take the lower and the upper bound. It's not that direct. Okay. Remember that H is bounded by delta I and mu I, right? Correct? Because it's the integral of the Hessian. That Hessian is bounded from below and above. So when you compute the integral, you get these bounds, right? Okay. So minus H will be bounded by minus mu here and minus delta, right? And then now if you do I minus that, and then before that, I have to put a nu, right? So if I put a nu, there will be a nu here and a nu here, right? And then I minus that, you will get 1 minus that, which is what you have here, right? You understand? Okay? So this matrix, which is symmetric, okay, it's, when we say it's bounded between this and that, okay, this came from the bounds we have on H itself. Okay, very good. So now, the spectral radius, come back to my question, right? What's the spectral radius of I minus mu H? You know the eigenvalues of I minus mu H, 1 minus mu the eigenvalues of H, but what's the spectral radius? Okay, it's not 1 minus the spectral radius of H. That's not like that, right? Because the eigenvalues of this matrix, they lie in this interval, right? Magnitude-wise, this could be larger than that, right? So that's why the spectral radius of this is the maximum between these two numbers, which are the bounds, right? Okay, and then the square. Fine? Understood so far? Okay. Okay. The spectral, this matrix, I minus mu h, right? Its eigenvalues lie between these two bounds. Okay. It's not necessarily the case that this upper bound, right? What do we have here? Sorry, okay. Remember, nu is less than or equal to delta, right? Mu is less than or equal to delta, okay? So this mu times nu is smaller than this, right? Is smaller than this, okay? So what do you have?
The right hand side is greater and the left hand side is smaller, so the bound is fine.
Fine, yes, the bound is fine, okay? Okay. I talk about this in the next slide. Let me get there, okay. Yes, okay. But anyway, on the face of it, if I have a matrix, right, which is bounded, I agree with you, we don't need, which is bounded like this, right? If there is no relation between A and B, this is what you can say about the spectral radius of H, right? It will be, okay, either A, magnitude of A, or the magnitude of B, right? Okay, that's what I'm saying here. Let's pursue this argument, and then in the next slide, I will tell you that actually I can only work with one of them. I don't need the other because of what we just said, okay? Because of the relation between this upper bound and that lower bound, okay? Fine? Okay, now. Okay, so this is, in the general case, the spectral radius of that matrix could be either this or that, the largest among them, okay? Very good, that's one. Now I can expand, so it's the largest of this or the largest of that. Now what I can do, if I replace this delta by the smallest it can be, which is nu, right? Then obviously this maximum is smaller than that, and this is the alpha I showed you before, okay? That's one way to do it, okay? However, yeah.
I think the problem with the above is that you can only, okay, 2.32 is valid only if the 1 minus mu delta and the 1 minus mu are both positive, right?
Sorry?
Are both positive. Because what if the upper bound, the factor 1 minus mu is negative?
This thing here?
Yeah.
Okay.
That's why we needed to apply the maximum, I think.
Okay, but here we are computing the square of the spectral radius. Okay, okay. So the square of the spectral radius is either this value, which is the square of one of these bounds, or the square of the other bound, right? So I agree with you, okay, that, for example, if this is negative and this is positive, magnitude-wise, this could be larger than that. Okay? Okay, so that's what motivated an argument like this, at least in the general case. But actually, like I show in the next slide here, it's enough for us to work with one of them. Why? Okay, look here. Okay, what do I want? I want this to be less than 1, right? Okay, so I want 1 minus mu delta to be less than 1, right? That will give me a bound on mu, right? It will give me a bound on mu like this, right? For this to be less than 1, it will give me another bound on mu like this, right? Which bound is tighter? Remember, mu is smaller than delta, so this bound here, right? As long as I choose this bound, this quantity here, okay, will be strictly less than 1, right? Will be strictly less than 1. So it's enough, okay? It's sufficient for us to work only with this bound here, okay? On the left-hand side, okay? You understand? Okay. So that's what I do here, you see. If I want the maximum of these two to be less than 1, it's enough actually to work with one of them. in this problem, okay? Because in this problem, nu happens to be lower than delta. But in general, if H is bounded between A and B and there is no relation between A and B, then of course, this argument here, you would have to carry it over. You understand? Right? If you have something like this where there is no relation between A and B and they can be, right? Then, of course, you have to argue like this. But what I'm saying in this particular case, because nu is upper bounded by delta, actually, right here, I can figure out, right, that it is this bound here that determines the spectral radius, okay? Very good. This first term that determines the spectral radius. So actually, from this argument, you see that the bound on nu for stability is 2 over delta, right? Whereas if you go back to the statement of the lemma, so I now got this, right? Whereas the lemma was giving me this. So which one is a tighter bound? Remember, nu is smaller than delta, right? So here you have 2 over delta times nu over delta. So this upper bound is smaller than that upper bound. So actually the argument, the second argument that I showed you, it shows that the algorithm is stable over a wider range of step sizes than I have stated here in the lemma, okay? So technically I can make this more, right, wider. Okay, but that's okay for us. I can leave it like this. For our purposes, as you are going to see, all we really care about is that a small enough mu exists that makes the algorithm converge. And if that happens, it will converge at an exponential rate. Okay? Okay, so this is the example. Let's come back to the mean square error example. Okay, the mean square error example. So what's the Hessian in this case? 2RU, right? So what is the smallest bound? 2 lambda min. The largest bound? 2 lambda max. So according to the theorem, if your step size is less than 2 nu, 2 lambda min, over delta squared, lambda max squared, you will converge at an exponential rate, right? According to the second bound, right, I found a more relaxed bound. If mu is less than 2 over delta, which is lambda max, it will also converge. And if you remember, this is the bound we get from a steepest descent analysis. If you study without knowledge of this lemma, if you write down exactly what the recursion is in the mean square error case, right? This is the new weight, old weight, step size. This is the gradient. Just write it down. This is the gradient, okay? And we know that the optimal solution, which makes the gradient vector equal to 0, satisfies the normal equations, right? So if you replace RDU by RU omega 0, so you will find that here you have RU omega tilde I minus 1. You can group these two terms after you subtract W0, right? And you get that the error recursion in this case, so you can do the calculation in this case directly, okay? Okay, so just before I continue, okay, sorry, this is not 2 over lambda max because delta is 2 lambda max, so 2 lambda max, right? So here delta was 2 lambda max and lambda min was 2 lambda min, right? So actually it becomes 1 over lambda max in this case. So here, what's the condition on mu for this to be stable, right? If you will get again 1 over lambda max, right? In 210A, when we studied this recursion, we were using in mu, not 2 mu. That's why we were getting 2 over lambda max, okay? But, okay. Here it is. And this is the bound, okay? Fine. So let's move on quickly to the second case here. So far, I only used a constant step size, right? Okay. But there are situations where a decaying step size may be useful to use. You're going to see it's not here, but I want to introduce it here so that you can compare the arguments, okay? So let's assume that instead of a constant step size, you use a time-variant step size, iteration-dependent step size, and the step size satisfies these two conditions. The step size sequence goes to 0, but not fast enough, so the series diverges. For example, 1 over I is like that, right? A sequence like this, tau, some constant over I plus 1, goes to 0. The reason why I write here I plus 1 is because starting from 0, we don't want to divide by 0, right? And the sum of this is infinite, right? So what I would like to show you next is that any step size sequence that satisfies these two conditions, this is just one example. In the homework, you have other examples that satisfy these two conditions. That any step size sequence that satisfies these two conditions will also make the algorithm converge. However, it will converge at a slower rate. Okay, you are going to see it will converge not at an exponential rate. It will converge at this polynomial rate, 1 over a power of I. Let's say 1 over I to a power. Nu is the lower bound, tau is comes from the step size constant. Right? Let's assume nu tau is 1. So this is 1 over I squared, which is slower than the exponential rate. So you might ask, so in the context of the gradient descent recursion that I'm studying here, you might say, so why use a decaying step size if I can get a faster convergence with a constant step size? And that's true. In this particular case, a constant step size will give you faster convergence. Okay? However, in the stochastic case, in the situation where I don't know J, I only know Q, and I have to replace the gradient of J by an approximation, in that case, a decaying step size will be helpful. Okay? You will see that in the next lecture, number 1. Number 2, but even then, a decaying step size has one disadvantage from the point of view of adaptation and learning. Because if this step size is going down to 0, as it is required to go down to 0, after it has become very close to 0, adaptation stops, because the influence of this term essentially goes down to 0. And if you are trying to estimate, for example, the minimum of a function that is changing with time, you're trying to track something, then that's a problem. Your algorithm will not be able to track, because by the time it needs to continue adapting, it has stopped adapting. So from the point of view of adaptation and learning, a decaying step size is problematic. That's why most of the time in this course, we will focus on constant step sizes. But I want to introduce decaying step sizes here and in the next lecture so that you see what you can gain, okay? Yes?
What if we make the step size be a function of the error instead of time?
Well, okay, there are many variations of this, right? There are many variations. People have developed many algorithms with variable step size designs where they have algorithms for adapting the step sizes as well, okay?
Convergence in that case?
Yeah, you can, of course. Most of these studies were in the context that I'm referring to, were in the context of stochastic gradient algorithms where you can show that they help improve convergence, okay? But like I said, even in the context of adaptive solutions, you will still face the issue that at some point, if this is required to go down to 0, the algorithm will stop adapting, okay? So for this reason, in this course, I focus mainly on constant step sizes, okay? So this lecture and the next lecture are, and perhaps in your homework problems, are some of the few times when you are going to see decaying step sizes, okay? So you have a question? No? Okay. So this is what I'm saying here, that decaying step sizes, okay, force the step size sequence to go to 0 and adaptation will stop. Okay, that's one. And on the previous slide, that the convergence speed will be affected. But nevertheless, let's work on it just so that you see what happens, okay? So I'm going to show that the error will converge at this rate. So convergence still occurs at a lower rate. Let me prove it, okay? This is the proof. Well, you have the same recursion, right, as before. I have the same recursion as before. In proof 2, remember? And then I group these two. I wrote them like this, right? And then I computed the norms. So now the only difference is that this mu will be mu of I, this mu will be mu of I. And then I bounded the norm of this squared by some alpha times the norm of this squared, right? The same thing will happen here. Except that now in the expression for alpha, it will be mu of I that will appear there, right? That's the only difference. The decaying step size will appear there. So this is the expression for alpha, expression 42. So to proceed to show that convergence occurs, I'm going to use this, this is splitting, which is very useful as you are going to see. Here I have 2 mu times nu, so I'm splitting it into 2 terms. Okay, into 2 terms. Why? You see, since mu is going down to 0, there will exist an I very large, right? Large enough I such that this mu becomes very small. Mu squared will be even smaller, right? So it's not difficult to believe that for I large enough, this negative value will be, this value, nu times mu, will be larger than delta squared mu squared, right? So that the negative and the plus ends up giving me a negative value, right? Okay, so alpha for I large enough is less than or equal to 1 minus nu mu. Because for I large enough, this dominates that and you end up with a negative, right? So that's okay. That's why I split. I split so that this takes care of that, and I can say that for I large enough, this is less than that. Good. Okay. So there it is. For I large enough, this is larger. Okay. And of course, also for I large enough, this mu is almost 0, very close to 0. So mu times that will be smaller than 1. So this condition will also hold, right? Okay. So therefore, I will get this. Okay. So I would like to show that this recursion is such that when mu satisfies the conditions I showed you before, the error vector will go down to 0. Okay. So the way you show it, okay, here it is. You see, if I iterate this many times, starting from some initial condition w tilde I0, start from time I0, okay? Start from this time over which this recursion is valid, right? And iterate this many times. What happens? At any time I, you will have a product of terms times the initial condition, right? Okay? So that's what I did here. A product of terms from time I0 times the initial condition. I brought the initial condition to the left-hand side, right? Okay? So as I goes to infinity, the limit of that ratio is upper bounded by that product, correct? Okay? Very good. So I could have written also, right? If you take the log of this, it's upper bounded by the sum of the logs of this. Okay? Very good. Now come here. I told you that this term here, okay, this term here, because mu is very large, I is very large, nu times mu, call it y, it's something that's non-negative and smaller than 1. And for the logarithmic function, this property holds. You see, if you plot a function, let's say this is y, so this is minus y. And if you plot the function ln of 1 minus y between 0 and 1, let's say this is 1, the function will look like this. It's lower. Okay? So the log of 1 minus y, this log is upper bounded by the negative of y. Okay? So I can replace this by less than or equal to the sum of mu I. Okay? So here it is. Take nu out. And now this sum, because the sequence diverges, right, this sum goes to infinity, right? So you have the log of something going to infinity, right, to minus infinity. So this ratio has to go to 0, w tilde has to go to 0. Okay, so this is one way to prove it. Of course, there are other ways. This is one way to prove that if your step size sequence satisfies these two conditions, the weight error vector goes to 0. But at what rate? Okay, at what rate? Let me show you now that the rate is the expression I showed you before, 1 over I to the power 2 nu tau. Okay, I will use a very similar argument. So remember that nu satisfies, so I'm going to derive the rate expression for sequences of this form. Okay, in the homework you will do other forms. Okay, a sequence of this form. So this sequence of course diverges, this series here diverges, and if you add the square values, you have a closed form expression for that, right? The sum of 1 over I squared, you get that sum. Very good. Again, for I large enough, right? For I large enough, this product will be larger than that. And for I large enough, the values of alpha will be between 0 and 1, just like before, right? Okay. So look what I'm going to do now. Before, I wrote that the log of the ratio is upper bounded by the log of 1 minus nu mu. Now I just kept all of it. Okay, because you see this number for I large enough, right? Okay, for I, this is larger than that. This is still 1 minus something, right? This is still of that form, like a y, and this y is also between 0 and 1. So you may ask, so why don't I just continue like before? You can. But you will get a convergence rate that's not as tight as you can get if you use this, as you're going to see. If you keep everything, you will get a better expression for the convergence rate. So I just kept everything. Now this becomes y. Put it here. Okay. So now you have a sum of two terms, the mu term just like before, and the mu squared term. Now, if we were adding all these terms up to infinity, this is pi squared over 6. So this is upper bounded by pi squared over 6. So I can't ignore this. And what about the sum of the 1 over I plus 1 here? Okay. So I ignored that second term, right? What about this sum? Remember, the mu is tau over I plus 1. So you get the tau here. And then the sum of 1 over I, but I made a change of variable. I added the 1 to the indices, lower and upper index, okay? Instead of writing I plus 1 here, I renamed that as an I prime, and that I prime now goes from I1 plus 2 to I plus 1, rather than from I1 plus 1 to I, okay? But now this sum here, this sum is upper bounded by an integral. Okay, why? Because of this figure. Remember, what's this sum? This is a sum of terms of the form 1 over I, between one limit and the other, right? Okay. And, okay. Because of this. Take this figure here, okay? This figure is the function 1 over x, like 1 over I, okay? So this is I1 plus 2, okay? So this value here is 1 over that, right? So 1 over that, you see, okay, and then I'm moving in steps of 1. 1 over that is the area of this rectangle. 1 over this is the area of that second rectangle, right? So this value here is 1 over I1 plus 2. And that value is the area of this rectangle, because the width of this is 1, right? So if I add the areas of all of these rectangles, I get that sum that I showed you, 1 over I from I1 plus 2 up all the way to, right? Where is it? This sum here, right? So that sum, the sum of the rectangles, is larger than the integral between this point and this point, right? Because the area under the integral is smaller than the sum of the... That's what I'm using, okay? That's what I'm using to bound, okay? So the area under the integral is smaller than that sum, fine? Okay? So that's what I did here, okay? So this is just plain algebra. And then, well, the integral of 1 over x is the log between these 2 points, okay? And this coefficient, I can bring it up here, okay? So then you have log of something less than or equal to this log plus that. So then that ratio is less than or equal to the exponential of this, right? Here it is. And then you can, the exponential of a log, you can write it like this, right? The exponential of the log gives you this to the power 2 nu tau, right? So you can see that the rate of conversion is w tilde I squared. Starting from this point, it's decaying at a rate 1 over I to the power 2 nu tau. Okay? 2 nu tau. So I get 1 over 2 nu tau. Okay, so the the convergence rate is of this order, right? Now, had you done like we did before, work without this additional term, okay, and without the 2 also here, that's what I did before. Had you done that without, without this 2, you would have obtained something like this instead, right? So actually it converges at a faster rate than what you would get if you continue using the previous argument. The previous argument was to show convergence, of course, and here also, this is again, by the way, I could have done everything uniformly from the start in one way, right? You would have obtained the convergence rate, right? And as I goes to infinity, this is converging. So I could have done everything together and make your life easier, okay? But fine. So to conclude, I'll show you the extensions to the complex case, okay? So I will not go through the details because they are very similar, okay? But similar conclusions hold in the complex case. So let me remind you of things you already know, right? So now omega is complex, right? So the function is still real valued. J of omega is still real valued, but the argument can be complex. Just remember that when the argument is complex, there are 2 ways by which you can define its Hessian matrix. You can work with omega directly or with the real case, with V, right? You take the real part, imaginary part of omega, and you collect them into a V. So you can work with the Hessian in the V domain or with the Hessian in, sorry, this is a typo here, in the omega domain, right? Okay, I should have written J here, okay, wherever you have. So, okay, you understand. Okay? I should have, there is a typo here. I wrote it in terms of G of Z, but in terms of J of omega, okay? Right? So this is the Hessian in the complex domain. They are related by a D and D star, okay? This J also, okay? And the gradient in the V domain is related to the gradient in the omega domain. Right? So, you see, so this slide summarizes the expressions we derived before. You can do all your analysis, all your thinking in the real domain using the V variables, and then you transform them to go from the Hessian in the V domain or from the gradient vector in the V domain. Just apply the D transformation. This is the D here, right? To go to the variables in the complex domain. Likewise, if you want to go from the real values V to the complex values omega, omega star, you also use the D matrix, right? So if you have this in mind, then every time I write something using the V domain, you can transform it directly to the omega domain, right? Just by coming back to this slide here, okay? I know lots of typos, but that's okay, okay? When I wrote this, I had G in mind, so. Another thing I would like you to remember, when we define strongly convex functions, okay? Again, I wrote it for G of Z, okay? That's okay. This will wake you up. This is how we define strongly convex functions, right? Minus nu over 2, right? For a new strongly convex function, you can replace all these z's by omegas. And then we said that this is equivalent to saying that the Hessian is lower bounded by nu over 2 in the complex case, or by nu in the real case, right? I'm just reminding you that there is a factor of 2, okay? And likewise, when you talk about Lipschitz gradient or upper bounded Hessian, if you say upper bounded by delta or by delta over 2, that will translate into delta over 2, right? So you see that whether you are working with real arguments or complex arguments, there is just a factor of 2 that appears, right? And that's why from now on, whenever I talk about a bound on the Hessian, I'm going to write it like this, delta over H. And whenever I talk about a lower bound on the Hessian, I'm going to write it like this, nu over H. Where this H is a variable that will be, if you are dealing with real omega, you set it equal to 1. If you are dealing with complex omega, you set it equal to 2, right? So you don't have to worry about this detail anymore, right? Once you settle on this convention, okay? So from this point onwards, that's what I will be doing from now on. So my function is strongly convex in the complex case. So it will be lower bounded by nu over 2. Earlier in this lecture, I talked about the real case that was lower bounded by nu. So from now on, I'm going to write the strong convexity condition in this manner, okay? Where I tell you H is the type variable. If you are dealing with real data, put 1. If you are dealing with complex data, put 2, right? Then we don't have to worry anymore about this. And the same thing for the Lipschitz condition on the gradient, fine? Okay. So, just like before, what are the conditions that I'm going to impose on the cost function now, on the risk function? The Hessian matrix is bounded from below and above by nu and delta, meaning nu over H, delta over H. Just like before, right? This is the quadratic example. So now if the variables d and u happen to be complex valued, you replace this by the magnitude squared. Under expectation, you will get this quadratic term. What is the Hessian now? RU transpose. It's block diagonal 2m by 2m, right? RU transpose, right? And it's lower bounded from below by lambda min of RUI, 2m, I of size 2m, and upper bounded by lambda max of RU, I of 2m, right? So this is the gradient vector. This is the Hessian, okay? Now, what is the gradient descent algorithm in the complex case? I showed you in the real case, right? It was W is the previous W minus mu, the gradient relative to omega transpose. Because it has to be a column, right? You differentiate relative to omega transpose so that you get a column that you add to the previous W to get a new W, which is a column. So I claim that in the complex case, when your argument is complex, you have to compute the gradient relative to omega star, not omega transpose, omega star. Okay? First of all, dimension-wise, this is consistent, right? Because this will be a column, fine? But why omega star? So, well, to prove it, let's think of the problem in the real domain. How would you think of the problem in the real domain, right? Think of J of V rather than J of omega. Right? If I had, okay, so let's introduce the real variable V. Let's introduce the real variable V. I don't know what that was. Okay. Let's introduce the real variable V. Okay. And consider the real version of the problem, right? Well, I can write down the gradient descent algorithm for it. We just talked about that in the first part of this lecture. The new V is the old V, step size gradient relative to V transpose, except that I'm going to use as a step size 1/2 mu. I'm free to choose mu. I'm going to choose it as 1/2 mu. We're going to see why, okay? Fine, I could use this algorithm, okay? As long as 1/2 mu, which is the mu prime I'm using here, is bounded by the bounds we derived before, this algorithm will converge to the minimum V0. Okay. So now remember that the gradient relative to V, right, of J, V has X and Y, right? So it will be the gradient relative to X transpose, right, of J, and the gradient relative to Y transpose of J, right? Okay. So this is here, VI, right? It should be a column, right? Yes. So you are paying attention. This should be a column, okay? Y transpose J, right? Okay. So here it is, right? This is VI minus 1, and this is the gradient relative to V, okay? Now, let's multiply from the left by I, Ji, and here, right? So you see, when I multiply VI by I, Ji, what do you get? What did you say? No, isn't W equals X plus JY? Right? Okay. So you get WI here, you get WI minus 1 here. What do you get here? You will get the gradient relative to X transpose, right, of J, plus J, the gradient relative to Y transpose of capital J, times 1/2. That's why I added the 1/2. What was this? If you remember, this was the gradient relative to omega star of J, right? So you see, from the gradient written in the real domain, you get the gradient iteration I wrote to you here in the complex domain. So that's why I write it W star, okay? So that justifies that, okay. Very good. And now you understand why I had to scale by 1/2. So if I have a gradient recursion in the complex domain, I can write down an equivalent recursion in the real domain where you replace the mu from the complex case by 1/2 mu in the real case, right? Just remember that. Now I can extend the results I had before to the complex case, because I can just restate these results for J of V and then translate them to J of omega, where omega is complex, right? That's all. And the proofs are like that. So for example, I can say that there is a small enough mu. For example, if the data is real, this bound you have here is exactly the bound we had before, mu less than 2 mu over delta squared. When H is complex, that's 2, so the bound becomes 4 mu over delta squared, right? So this bound captures both situations together. The error will still converge exponentially, and this is the expression for alpha, and I already wrote it in a form that captures both cases together. If you put H equals 1, it is what we did in the real case. If you put H equals 2, is what you will get in the complex case. Okay, so how do you prove that this is true in the complex case? You already have the idea, right? So all you have to do is, let's write down the recursion, the corresponding real recursion, right? We know that this is the real recursion with mu prime equals mu over 2, that this recursion is equivalent to the complex gradient recursion we are studying, right? Let's write down the conditions for this. What were the conditions for this? Its mu, here it is, its mu is this, right? Less than, what was it? 2 nu over delta squared. So you get 4 nu over delta squared, right? Which is exactly what the theorem says. You get the bound. And what was alpha? Alpha was, in the real case, alpha was 1 minus 2 mu prime nu plus mu prime squared delta squared, right? If I got it correct, right? Now replace mu prime by mu over 2, or mu over h, right? Mu over h, that's exactly right, this statement. You get it? Okay, so proving the result in the complex case. So it's not always that I will be doing this, right? But I want you to see it at least once, that, and get convinced that moving from one domain to the other is not that difficult. But there is this discrepancy of this h that comes up. It just has to be there, right? Okay. So that's for constant step sizes. And then you can similarly extend the result for the decaying step size case, right? For the decaying step size case, you put the mu of I here. Again, you can show that if this mu of I satisfies both conditions, the series doesn't converge and mu converges, that the algorithm will converge, and you also have an expression for the convergence rate. You have the H there. How do you get it, right? You just get it from, right? Just write it down for the, I think I have it here, right? Just write down the recursion in the real case, use the fact that this is mu prime and go back, right? You will get this bound. Fine? Okay. You might ask, for example, since everything now is complex valued, omega is complex valued, right? Does it help to use a complex valued mu? I kept it real here, right? That was an exam problem last time, okay? It's a homework problem this year, okay? You can try it and find out what the answer is. Of course, you'll be getting answers to these problems, right? But it's a useful question to ask. Does it really make a difference, okay? Fine. So you get the idea. So what I did today, let me see if there is anything else. Okay. So what I did today, right? I focused on the optimization problem, right? Just a quick summary. And J wasn't an arbitrary function. It is strongly convex, right? I assumed that it is strongly convex. Strongly convex, sorry. And has a Lipschitz gradient, right? That meant its Hessian is bounded from above and from below, right? And then we showed that if you use a gradient descent algorithm like this, relative to W transpose, if mu is small enough, and I gave you a bound on how large it can be, right? Exact bound. The norm of the error squared will converge to 0. So you converge exactly to the minimum. And not only that, it will converge exponentially fast, right? That was one conclusion. And then I said, if I replace this by a decaying sequence satisfying the two properties that the series diverges and it goes down to 0, it will continue to converge, but at a lower rate, and I gave you an expression for that rate. It was something like this, okay? Power of I, right? Some power of I. Okay? And then I extended this to the complex case. The recursion was exactly the same, except that this omega was replaced by omega star. And then you got similar conclusions that for mu small enough, it converges exponentially fast. And even if you use a decaying step size, it will also converge. And then I made the remark that in this context, in this particular problem, right, it's more advantageous to note that if you use a constant step size, the convergence rate is faster. The reason why I'm showing you a decaying step size now, it will be more useful in the stochastic case, but I'm introducing it now so that you see how it changes the dynamics, okay? And to show you some results that will be similar to results we'll be discussing later, okay? So this is what I wanted to discuss with you today. Do you have any questions? Yes?
We didn't say why mu, let's say, decays exponentially.
If mu?
If the sigma of mu doesn't really go to infinity.
Okay.
For
No.
that case, it won't converge, right? But we didn't say why.
No, okay. I didn't say that. I don't remember making that statement. What I said is, right, if your steps, and this is not if and only if, okay, not if and only if. What I said, pick a step size sequence that satisfies these two conditions, okay, so the sum of mu goes to infinity and mu converges. Under these two conditions, I can show that the algorithm converges, okay? Now, what I said is that this, why this makes sense is, this is saying that the step size should not converge fast, right? Because if the step size converges very fast, you didn't have enough time to learn what the minimum is. That's essentially, right? If this you see, if this sum For example, if you take 1 over I squared, this goes to 0. Okay, but this is not infinite. This will be finite, and 1 over I squared converges to 0, right? For your problem, that convergence to 0 may be happening fast enough before it reaches the omega 0. Okay, so what this condition is ensuring is that your step size is going to 0, but not too fast. You are giving the algorithm enough time to learn. Okay. And then, of course, there are other conditions, some of them in your notes. The step size doesn't need to be of the form 1 over I. You can choose other constructions, okay, with other powers of I, and show that you get convergence and different rates and so forth. Okay? Good? Okay, so we'll conclude here today.